All right, hey everyone. So this is the walkthrough and a little bit of pre-lab for Lab 4, dealing with molecular shapes and valence shell electron pair repulsion theory. Okay, that's the VESPR, uh, as abbreviated. So just let's go through a couple things I want to look at before we get into it. So on your Cougar View, I've put a link to drawing Lewis dot structures and a link to a VESPR introduction. So both of these are pretty much all you're going to need to do this outside of this chart here. So let me pull this up. This chart should have everything that you need and cover every shape that you will see. So we'll talk about how to use this chart here in just a second. I'm going to show you some examples, maybe work through the first one on Chem 21 so you can kind of see how it works. So there's no videos, no pictures or anything for this lab. A lot of this is you can kind of call it independent research, or if you understand the concept and the topics, you can just kind of roll through this without any trouble. Okay, so let's talk about what we're going to be doing in this lab first, kind of the pre-lab, and then I'll take you to Chem 21 and talk about um, how you fill out those worksheets and lab reports. All right. So let's first talk about Lewis dot structures. Actually, let me get a periodic table ready. So we've talked about valence electrons, right? The valence electrons are the outermost shell of electrons, and typically you can find out how many valence electrons an atom should have by which group number they're in. So hydrogen in group 1, along with lithium, sodium, potassium, rubidium, all of those have one valence electron. Group 2, starting here, beryllium, magnesium, calcium, strontium, all of those have two valence electrons. Skip the transition metals because they will typically tell you what their charge is, either by what they're connected to or the Roman numeral in their name. Okay, so like copper 2 is has two valence electrons, which are given up to make a copper 2 plus ion. Remember, if I give away electrons, I get positively charged, so copper 2 ends up becoming copper 2 plus as an ion. Copper 3 has a Roman numeral 3 behind it, will become copper 3 plus and have three valence electrons. So typically, it's like whatever they're linked to is a better measure of how many valence electrons they have. If it's linked to a chloride, for example, we know that it only gave one electron to that chloride because the chloride is in group 7. So it only needs one electron to get to this noble gas configuration. All right. So, and we've kind of worked on this before, so this shouldn't be something new to you. Just know that when you're looking at groups and counting valence electrons, you skip the transition metals, go straight over to boron. This is group 3A, and it has group 3. All elements in group 3 have three valence electrons, so aluminum, gallium, indium. Carbon 4, nitrogen 5, oxygen 6, fluoride 7. Okay, and everything below it follows the same pattern as the one up top. Okay, so now that we've established that, let's look at how to draw the Lewis dot structure for those. Okay, so let's just pick one. Let's say nitrogen, since it's sitting right there. All right, so for nitrogen, the first thing I want to do is start with the chemical symbol N, and then it has 5 valence electrons because it's in group 5, we've already established. So you'll draw these in kind of clockwise and put them at each pole. Okay, what I mean by the poles is north, south, east, west. Okay, so go clockwise one at a time and put them at each of the poles. All right, so now I've got my 5. This is what the Lewis dot structure of a neutral nitrogen atom looks like right here. Now say I wanted to combine it with something. We just mentioned chloride, right? So let's draw chloride up here. Bop, bop. I'm putting these 7 valence electrons, and typically I would just go clockwise, but I kind of know where I want this single electron to end up. I want it to be on this side where I can connect it with the single electron on this nitrogen. Okay, now before I do that, let's work a couple more over here. Make sure y'all can see that. Yeah, okay, so I'm going to put another chloride over here. With the 7, and then we'll put another chloride right here with 7 as well. That's 7 valence electrons. Alright, so now imagine that they want me to connect all these. Let's say they gave me a formula. Oh gosh, that's ugly. Hold on. They gave me a formula at the beginning of my problem. They said it was NCl3. Okay, and I need to figure out how to draw a Lewis dot structure. I don't even think this is a real compound, but let's just carry on like it is. So now I want to figure out the total number of valence electrons I have available. Okay, so we have 7 from each chloride. That makes 21. 7 times 3 for the chloride. I'm going to put chloride here with a little dot. That's not a good thing to put because chloride and then nitrogen equals 5. Chloride is 7 times 3, which equals 21. So I have 26 total valence electrons in this compound. Okay? If there's no charge, if they didn't put a minus or a plus right there, then you're just going to have whatever number of valence electrons each atom should have. Okay? Once you see a minus or a plus, that means you're adding or take away electrons after the fact. Alright, so now we got 26 valence electrons. I'm going to connect my chlorides, all the singles to the singles, and I'm going to create a bond. Okay, so let's do that. New, don't save. Now I'm going to put my lone pair is still there on the nitrogen, but now I have bonds that connect it to 3 chlorides. Alright, and we'll fill out the lone pairs that were still on the chloride. One, two, 3, 4, 5, 6. Alright, so now I had 26 before I made my molecule. I need to have 26 after I make my molecule. So this is where the bonding comes in. If I double bond it or triple bond, it takes or donates electrons to the total count, right? And it also creates charges. So here's what we're going to do. We're going to start with 26, right? So now let's count how many we have here. I have 6 around there, 6 around there, 6 around there. That's 18. 20 in lone pair electrons, and then 2 for each bond, so that makes 26. 26 electrons. So that is correct, right? Now I want to figure out the shape of the molecule. This is where you'll go to your chart. Let me pull that up. The chart was right here. Alright, so let me go back to the paint program and just let's count. So the chart has there, what's on the left? Number of electron groups. Okay, now this is always concerned with that central atom. So in this case, the nitrogen is the central atom. It has a lone pair is considered an electron group, and a bond is considered an electron group. A double bond is still only one electron group. Okay, so there's 4 electron groups around the central atom. I'm going to take all these circles away. 4 electron groups around the central atom. So I'll start there, and I'll go down on my chart to number 4 right here. All right, now I want to identify the number of lone pairs in the molecule, right? Lone pairs are these little single dots of electrons, or excuse me, pair of dots of electrons um, around the central atom. So there's only one lone pair. A pair is two, correct? So let's go back to our chart. Sorry, I spent more time transitioning and doing my OBS stuff than I can. So 4 electron groups, 1 lone pair. You're going to have a trigonal pyramid. All right, this is the shape, and here are the angles that are each bond is going to be at. Okay, 109.5, 100.7, depending on what your central atom and what the constituents around it are. Certain constituents are bigger, and so they push more away from the electrons, stuff like that. So anyway, that's how you use your chart, and there's all different kind of examples. Water, for example, is 4 electron groups with 2 lone pairs, so it ends up becoming bent. And you can just kind of play around with this. And there's also websites. So let me just see. Let's just type in ammonia molecule. And you see, if you type in any of these molecules, they will show you the shape or the number of valence electrons, or so you can kind of, like I said, independently research each of these molecules and get the answers that you need. So what I mean by that, let's go take a look at the lab report sheet. Move this over here. Okay, so I haven't filled out anything. This is I work these lab reports as well, so I don't always answer them in front of everybody just because I don't want to give away the answers. But let's just do this first one together. So compound 1, calcium chloride. All right, the first thing I want to do is determine the number of valence electrons. So let me just kind of show you something. It says to upload an image. Some of you may have trouble doing that. Like I can do you can do the paint program, obviously. So I could draw calcium chloride. Let me get rid of this. Let's say calcium and chloride. I'm going to put my chloride on each side because I assume they're connected to the calcium. The center atom is usually the cation, the positive, more positively charged atom. Not always though. Okay, so like I said, you can look this up and see what the molecule should look like and everything. You can probably get all the answers you want, but I recommend doing it yourself because you can do everything here without help. Okay, I promise. We've covered everything. If you don't understand a certain topic, you can email me or go back and look at your lecture PowerPoint or lecture videos that I provided. For those of you not in my class, like I said, you can email me and I can send you a link to whichever part you're having trouble with. So before I do that, let's get the total number of valence electrons, right? I have a calcium and 2 chlorides. I know from what I just did that the chlorides each will have 7, and then I can go to my periodic table and find out how many calcium has. Calcium has 2, right? Group 2, so 2 valence electrons. All right, so the total will be, I'm going to put my electrons around this. 1, 2, 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. All right, so easy enough. I have a solo electron on the calcium, solo on the chloride. Those connect, and now I have calcium chloride out one side and a chloride out the other, and then my valence electrons 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So let's check and make sure I have the same number of valence electrons. 7, 7, 14 plus 2, that'd be 16 there. 6 around the edge, 6 around that edge, that's 12, 13, 14, 15, 16, 16 there. Okay, so 16 valence electrons. That is correct. So it looks like my molecule is drawn correctly. Now I'm going to use that chart to identify what the shape is. Okay, so calcium's my center atom. I have 2 electron groups beside it, right? There's no lone pairs. All I have are the 2 bonds. So that's 2 electron groups, 0 lone pairs. 2 electron groups, 0 lone pairs. Let me transfer over there, go back to my chart. 2 electron groups, 0 lone pairs. The molecule is linear. The angle is 180, right? So going to go to Chem 21. As it goes for Lewis dot structure, what I might recommend is doing this. Calcium chloride. I didn't mean to do that. Let's do structure. So where's a Lewis dot structure that is completed? Right here. Okay, so I could say download that or copy this image here, right? Copy image, come over to this, edit answer, choose file. Let's see if I can paste there. Not, so I'd have to save the file and then paste it in there. I would probably do it on my paint program, like trim this right here. Crop, boom. Right now I've got this image by itself. I can save that image and then upload it onto my lab report. Oh wait, I didn't show y'all. So I came over to the paint program and clipped out that image of the calcium chloride. You can draw it up and make it prettier. If you can't find it on the internet and save that image, so you could save the image. I'm not going to do it. I'm not going to go through all that, but just know that you can go find the image, save it, download it, whatever you got to do, draw it yourself, save that picture, and then upload it here onto Chem 21, right? So that's how I would do it. Everything else you should be comfortable with. Number of valence electrons available. Go back to my paint program. We said 16, right? So 16. Submit. Next. Number of bonding electron clouds around. So the clouds are the same thing. Lone pair counts as one cloud, and any kind of bond, double, triple, single bond counts as one cloud. Okay, so bonding. Oh, this one's bonding electron cloud. So that's 2 around the calcium chloride. And then next problem, non-bonding, there were 0, right? Lone pairs of electrons. The geometry was linear according to this chart, right? 2 number of electron groups, 0 lone pairs, linear, 180. There, linear, submit. Next, molecular. So the difference between electron group geometry and molecular geometry is the actual shape. So the electron geometry is however many number of electron groups. Okay, so if it asks you the electron geometry, the best thing to do is just say how many around the central atom, and then act like there's 0 lone pairs. Okay, so all electron geometry for those that have 4 electron groups will be tetrahedral. The molecular geometry is what's here. So if I have 1 lone pair, the molecular geometry will be trigonal pyramidal. The electronic geometry for 4 and 1 would still be tetrahedral. Okay? Because it's counting in the lone pairs of electrons. I don't have a good example of that right offhand, but so for this one, they're both the same. Linear, linear. Next problem, bond angles 180. Submit. All right, so there's the first one. You'll get to see a little bit of everything throughout this lab, so you'll see pretty much all of the different examples up to tetrahedral. Okay, so up to 4 electron groups. You'll pretty much see all of these shapes and variations. You may see some 5 in the post lab questions. I'm not real sure, but just if you get hung up with anything, you can obviously let me know. Just so last thing I'll mention one more time, there's a difference between electronic and molecular geometry. Electronic geometry takes into account lone pairs of electrons. The molecular geometry is just concerned with the atoms. Okay? If it's a lone pair on top of a nitrogen, the molecular geometry is just concerned with the atoms. Okay? So I think that's about it. Let me go back and look at the lab real quick. I think most everybody has done pretty well with the material. It's just getting the answers in, right? You get fed up and it says that it's wrong or it's not within the tolerance, and then you go put in, some bad numbers, and then so that's what I end up seeing are the bad numbers that you put in after the fact, after you missed the first one. Okay, so just if you get hung up, if they say it's not right, send me a picture, and I will look at the problem and try to see if I can't get you straightened out before you miss all of the attempts. Okay. So I think that will be it for today as far as the walkthrough and the pre-lab. As I said, there's also many videos out there on YouTube that you can kind of look at and try to get more familiar with molecular geometry. Um, but this lab is pretty straightforward, right? There's no videos, no pictures. You can just kind of go through it at your own speed and work the problem how you need to. Like I said, I use the paint program to do my Lewis dot structures, but that's because I want you to see how it's worked, okay? So you can probably just go copy and paste all these, but I would recommend trying to get into practice yourself, right? Draw it out and then check the images on Cougar View to see if it's correct. All right. Um, yep. So that is it. I will see y'all next week. We're getting ready to do midterm review and lab midterm. So stay up to speed. Keep up with your work and make sure that you have everything turned in on time so we can hit the midterm with all the knowledge we need. Okay, that's it. I'll see y'all tomorrow.